Hey guys, today I'm going to walk through a paper that I wrote about 2 months ago. The reason I wrote it was because since 2019, in the event of the coronavirus outbreak, there's been kind of a quieting down of the quantum computing literature. Um, so I thought, why not just kind of write a new update on it? I think it was about 5 years ago when the last update on quantum computing was written. So I thought this was pretty apt to just continue that in the science community. My focus for the paper is updating on quantum computing in the medical and biomedical research realms. So before we even get into it, it's like, why am I writing about quantum computing? Well, the reason I'm writing about it is because I've always had this kind of technical background. I took AP Computer Science in high school, standard Java, and then next year I learned HTML, CSS. The year after that, I learned Python. Right now, I'm working on a machine learning project through Brigham and Women's Hospital. It's a research project kind of studying cardiac scans, shooting out results. So it's the scan positive or negative. So there's a lot of computational kind of background that I have. And I'm also an entering medical student, so I thought it'd be pretty relevant to write about it now. So with that, we can dive right into the paper. Okay, so essentially, like I talked about before, the paper is a good overview about what has happened in quantum literature so far, what are the kind of breakthroughs, and where are we going. Since the end of 2019, there's been very, very promising results in the quantum computing realm, especially in this new kind of gate-based method for quantum computing, led by companies such as IBM, Google, and a whole bunch of others are starting to jump on board. So there's definitely kind of like a quantum computing kind of revolution happening, so it's definitely worth exploring. Yeah, so of course, I'll probably end up linking this paper below in the comments section, kind of in the description maybe, and then we'll get right into it. Before I even get into it, let's just remind you guys to like and subscribe, and let's get started. Okay, so before we can really talk about quantum computing, we have to talk about its benefits, right? So if you think about classical computers, the computer you're probably watching this on right now, you have kind of a chip in the computer, sort of and the chip has a whole bunch of different components on it that run different parts of the computer. So you can have a graphics processing unit, which focuses on the graphics, so makes your screen what the screen is. There's a computer processing unit as well, CPU. That does is kind of run the numbers. It's basically a calculator for your laptop or computer to make sure all of the kind of streaming that you do, all the calculator functions, all of the logic that's required in the computer exists. There's a whole bunch of other parts, but I won't get into that. So basically what quantum computing is doing is kind of addending kind of like the existing computational limits of a CPU, the computer processing unit. So what you have on your CPU nowadays is something called a bit. So what a bit is short for binary unit. So a bit on your CPU is basically a switch that either goes from 0 to 1. And based on if it's 0 or 1, it's like an on or off. And you can have a whole bunch of those bits on one CPU, right? So if I want to spell my name, there's a way in binary kind of language to write my name in zeros and ones, right? There's also a way to encode that, encode numbers in bits from 0 to 1, etc. So there's a lot of storage information that can happen in bits. So that's why bit is important. What quantum computing does is it provides an additional advantage. So unlike a classical bit where you only have 0 and 1 states, quantum computing, as you can see in this diagram below, essentially that kind of translates to between 0 and 1, you can have infinite amount of possibilities for different states. So it's not just 0 and 1 anymore in quantum computing, it's actually 0 through 1. So there's infinite amount of states between 0 and 1. So there's a huge benefit there. So instead of storing things of just 0 and 1 across many bits, so 0, 1, 1 for the first bit, 0 for the second bit, 1 for the third bit, etc., for like thousands on thousands of bits, now you can just use kind of one quantum bit or a qubit that can store one value. Say you want to store the value 0.18, right? or 0.19, you could store that on one quantum bit. You don't have to kind of translate across multiple bits to store one value. So there's a storage kind of almost infinite capacity with qubits that a lot of people are trying to exploit nowadays. And storing these things can exponentially speed up the number of processes, the computational speed of a lot of calculations, and of course, whatever runs on your laptop computer. So that's kind of the introductory paragraph. Kind of covers like the difference between classical bits versus quantum bits. And then this paragraph here is just a good overview of an example of what are the benefits. Very classic example of why classical bits kind of are inferior to these n-bit strings of quantum bits. Okay, so with this process called amplitude amplification, it kind of just exploits that same property that I just talked about. And say we were searching across for a solution, so 1 + 1, right? And we wanted to do that in a normal computer, classical computer. It would take 2 to the n, n being the possible number of solutions, of order of 2 to the n to actually find that solution. While in quantum bits, it would only take the square root of 2 to the n. So the time that it takes to solve that solution is much lower, dramatically lower. And these numbers only come from Grover's algorithm. Of course, there's other ways to kind of compute this. Grover is kind of a guy in the 1990s who's super smart, pioneered kind of the path for quantum computing, and just understanding kind of like the logical functions behind it. Okay, so before we kind of carry on with the rest of the paper, I think kind of covered, I guess, a good summary of the difference between classical versus quantum computing. Now we'll just kind of talk about these two ideas, so quantum advantage and quantum supremacy. So quantum advantage is essentially saying quantum computing has a relatively faster processing speed than classical computers. And quantum supremacy says that quantum computers can solve problems that classical computers cannot. So quantum advantage has been proven, or has happened because of what we'll talk about in a bit. Quantum supremacy has not been proven yet. So it hasn't been proven that quantum computers can solve problems that classical computers cannot. So there is kind of a difference there. But recently, they've put in a whole bunch of different types of problems into quantum computers. And, there have been claims that quantum supremacy has been reached. But of course, there's always pushback to it. So now that we're talking about, now we have a good understanding of the logic behind quantum computing, we can kind of jump into the idea of quantum annealing. In current quantum computers, mostly in the science fields, this process of quantum annealing takes place. There's other ways to kind of use quantum computers, but quantum annealing is kind of one of the upfront kind of techniques that a lot of people use because it's been worked with a lot. So to understand quantum annealing, we'll just talk about two other factors. So coupling is one of them. So what does that mean? As you can see in this diagram here, let's see if I can zoom in. Yeah, perfect. Okay, these are two qubits, so quantum bits, right? 1 and 2. Coupling essentially just guarantees that you can have two states together. So in this case, if this is state 0, then this will also be state 0. State 1, this will also be state 1. If this is state somewhere in between 0 and 1, this will also be between 0 and 1. So essentially, coupling just guarantees that two quantum bits will be in the same state. So why is that relevant, right? It's relevant because I'll explain with this chart. In this kind of graphic here, in A, we can see essentially superposition taking place. So the quantum bit can either exist as 0 and 1 or states in between. B are kind of these energy wells. So think of the energy well as kind of a landscape which can help you find your solution faster, right? So, in standard chemistry or physics, we learn about Gibbs free energy. You've probably seen energy diagrams. And essentially what you're trying to do is minimize the amount of energy in the system. And you do that by detecting where's the lowest in the energy well, right? So if there's one solution, this is kind of the energy well that takes shape, right? Essentially, there's only one state that can exist in the bottom of the well. Here, we have two possible states or solutions to the system. So we have two different kind of, qubit values that are possible. Number three, there are two solutions, but we can see there's a global minimum here, right? So the global minimum kind of shows that despite there being two possible states, the global minimum points to the most likely state or the most likely solution to the problem. So combining the aspects of this energy landscape and coupling, we can create something called a biased landscape. So essentially what that says is that assume there's four different solutions for this biased landscape, right? And to solve the problem, we need two qubits. So that's why you see 0, 0, 0, 1, 1, 1, 1, 0. What coupling kind of helps you do is create a biased landscape so that you know you need two qubits. So you can tie these two qubits together, and given the number of qubits, given the number of solutions, it will help you better find the final answer. And so here we see the final solution entails having two qubits of one value, one each. So in some sense, that's kind of like the basics of how to approach quantum annealing, right? But what it really kind of boils down to for quantum annealing is the advantage it has over standard classical computing. So in the classical computer, you can do annealing on a classical computer, but it's something called thermal annealing. So in this diagram here, we see that thermal annealing is essentially, if we let a ball loose in the system, right? So these two are, well, this is one ball here. If we let the ball loose, eventually it would try to find kind of like the global minimum of this system, right? So it would just roll around until it finds the bottom. Thermal annealing in a classical computer essentially just goes over that energy barrier, right? So kind of just hops over. And hopping over, it hops over and eventually finds a solution. But quantum annealing kind of takes advantage of the property of the superposition of quantum states. So it can be anywhere between 0 and 1, and it can kind of just phase through the energy barrier. So in that sense, we're literally phasing through the energy barrier and reaching the lower state faster than thermal annealing. So imagine a system not in a 1D plane, but in a 3D plane with millions of possible solutions. Hopping over the energy barrier, actually like putting in the energy to do that, requires a lot of computational power, computational time, while phasing through the energy barrier takes a lot less energy and a lot less computational time. So there's huge advantages to quantum annealing. Okay, so quantum annealing can kind of do two things, and these are kind of places where they're headed right now to improve upon current quantum annealing processes. One is called simulated annealing. Like I said before, this process here, thermal annealing, also goes by another name called simulated annealing. So essentially, we're simulating a quantum annealing process just in a classical computer. Recently, there's been kind of headway made on how fast quantum annealing can happen. And one of those ways is something called gate-based methods. And so what gate-based essentially does is, if you look at this biased landscape here, gate-based, instead of kind of checking all the solutions and making sure each one is either valid or not valid, or one's better than the other, gate-based methods provide logic behind jumping different states, right? So if I'm in this state here, would I rather go up a state or down a state, right? So a gate-based system will say, if I'm in the middle here, why would I jump up an energy level when my purpose is to minimize my energy level and find the solution? So instead of jumping up a level, the gate-based system would say that is false, don't do that, while jumping down a level would be more looked upon, right? So essentially, I'd kind of make the jump and just go straight from here to here. So gate-based is kind of just logical thought behind the quantum annealing process. And so that's what tech companies are trying to push towards nowadays. Okay, so let's talk a little bit about quantum computing's relevance to medicine. So one, it'll improve methods based on biophysical molecules and biochemical processes. Two, it introduces methods that can navigate big data, which can characterize genomics, health systems, etc. So what do I mean by that, right? So number one, we'll kind of look at the biophysical side of things. So USC has used a D-Wave computer, which is one of the industry standards for quantum annealing. And they've kind of looked at transcription factor binding affinities along DNA. So as you know, DNA has 4 billion plus base pairs in every kind of cell in the human body, and identifying first how to quantify those kind of parts of the DNA is computationally expensive because there's 4 billion base pairs that exist in the DNA. So just putting that into a chip is hard enough. But what they're trying to do is figure out where a transcription factor best binds along that DNA. So that can be broken down into many computational parts. So one is like identify what the transcription factor is, how does it look, what are the protein components of it, or protein makeup of it. And then 2, where does it bind along that DNA? And then 3, where does it best bind along the DNA? And then 4, what transcription factor best binds to which location on the DNA, right? There's a whole bunch of different layers to that problem, and that definitely takes a lot of computational, again, speed and time, and a lot of that's needed, right? So classical computing probably can't do that as well as quantum computing. And so they've done these tests, and they've kind of used quantum computing to their advantage, especially in achieving solutions in clinically and experimentally relevant timeframes. Of course, the work that they're doing has a lot of timelines and regulations to meet, so they want to get it done as fast as possible. So they found advantage in quantum computing. There's another example here from University of Michigan. They kind of do the same thing, but instead it's with medical device. And they've definitely found a lot of advantages to quantum annealing, kind of using quantum computers. And now they're actually looking towards using gate-based systems to kind of speed up the process even more. Okay, and then just to touch upon relevance to medicine, especially in terms of navigating big data, like I talked about, human DNA has over 4 billion base pairs, so that alone is kind of a task to compute and analyze what parts of the DNA kind of overlap with each other, kind of see different avenues for DNA kind of manipulation. But we're going to talk about big data that exists in almost every field, so finance, medicine, of course, sports, any field that you can think of probably has some kind of element of big data. And so big data, essentially what that means is, whole collection of data, data points across every second, every minute, every hour, every week, across many, many years, right? So in that, you have more than a billion, more than 10 billion, more than a trillion data points. And so classical computers find it really hard to take in all of that data and kind of compute it. Well, quantum computing, since there's infinite states between 0 and 1, you can kind of just condense that data and store it on less kind of qubits than normal bits. And you can also use these quantum annealing methods to kind of process the data way faster than you could with classical computers. So, for example, if I was a patient at a hospital and they hooked up a blood pressure machine, heart rate monitor, took blood tests, just say they had those 3 things. And the heart rate, of course, changes almost every minute. You could record it for a minute and then record it the next minute, record it the minute after. Blood pressure, if you want to take it in increments that are every 10 seconds per se. And then a blood test, say you take that every 2 days, right? Every day. And you wanted to track the significance between changes in heart rate, blood pressure, as to the proteins in your blood sample, right? Doing that alone, kind of adding up all those data points across, say, a 3-month study with 150 patients. Just in that, you have so many data points. For if you take a data point every minute, that's 60 minutes in an hour, 1,240 minutes in a day, times that by 365. So many data points. Okay, so now that we kind of talked about the quantum annealing method, let's talk about where we're going. So quantum annealing has been improved for the past 10 years, but now we're kind of reaching the point where we can do better. So nowadays, companies have started shifting towards the idea of gate-based systems, like I mentioned before. And so with gate-based, you can start kind of simulating things in the real world. So if we're looking at protein interactions, protein is just literally a sequence of amino acids, but the way they fold with each other, kind of unpredictable. But using quantum simulating, how to predict how they fold. And if we know how they fold, we can predict how they interact with other drugs, other things like that. So there's some drug discovery avenue that could be explored there, for example. So that can only really happen with gate-based. Why? Because you can tell the computer, there's different parameters defining the solution, right? So instead of hopping every solution, you could tell the computer tyrosine is polar, right? So if the tyrosine amino acid is polar, therefore will only interact with non-polar amino acids, right? So in that, there's some logic behind finding the solution. And so that can only be achieved with gate-based systems and much faster. Right? So we're really only in the first era of quantum computing, quantum annealing. We're trying to jump to quantum simulation through gate-based systems. And eventually we'll reach this idea of a universal quantum. So essentially just reaching that quantum supremacy kind of realm and just far outweighing the advantages of classical computing and beating all supercomputers out there, etc. So as of now, there's some kind of setbacks with these gate-based devices. One big setback is the quality of the qubits. So just being able to control the qubits and telling them where to go or giving them the logic behind where to go is a very difficult task. Why? Because just as we can see, there's so many different states between 0 and 1 that a qubit can be rested in. And so if there's infinitely many states, it's hard to control exactly which state the qubit's going to be in. And also telling it how to move across the energy landscape is even more difficult. That kind of noise problem or quality problem can be defined as the noise that's produced in the results. And a couple of scientists, papers I'll link below, have kind of deemed this era that we're shifting from standard quantum annealing to this gate-based annealing methods as a noisy intermediate scale quantum era. So essentially, like, noise exists because of the number of attempts to increase the number of qubits as well as control the number of qubits. So, of course, like I talked about before, there are a couple companies that have started achieving these gate-based systems. So D-Wave before produced a quantum annealing machine. They say it has over 2,000 qubits. Super hard to do. So we can kind of see that here. So this orange line is kind of like the trend for just normal quantum computing, quantum annealing computers. While blue is the trend line for gate-based computers. And then to note that gate-based computers are much quicker than this, the industry standard quantum annealing. And both seem to be taking almost exponential paths every year to definitely increase the amount of qubits and therefore increase the amount of computational speed on each chip. So this has been dubbed Rose's law, kind of like the exponential growth of qubits in a quantum chip. Similar to, you might have heard Moore's law, which is on classical chip. Essentially, it's saying the number of transistors on an integrated circuit will double every 2 years. Right? So that would be a linear relationship, but right now we're seeing kind of an exponential relationship in these qubits. But yeah, so big point here, this paper, just a good overview. 2019, Google launched Sycamore, which produced over 128 qubits in a gate-based system, which is incredible, right? And so gate-based, again, is much faster than quantum annealing and much faster than classical computing. So we're on the verge of something new here. So I thought it was worthwhile writing about, and I hope you guys enjoy it.